So today we are gonna talk about the concept of analytic continuation. So if I ask you what's the value of sine of tree, you'll just put in a calculator and figure out the value of it. But what if I ask sine of 3 plus I? So you must learn in the trigonometry that sine of this theta is equals to this opposite A divided by hypotenuse B. Sine of theta is equals to A by B. But if theta is an imaginary number, we can't find how A and B would be like. So they introduced a concept called analytic continuation. So this is a line and it's real axis, and this is complex axis. If I write a function f of x equals x squared, I can easily define this x squared in all over this complex plane. It's like if I put in f of I get I squared, which is nothing but minus 1. So we can find the value of the quadratic functions, but we can't find the value of trigonometric functions when the input is imaginary number, like f of x equals sine x. So what we are gonna do is we are gonna convert this function into a normal polynomialic function by using our Maclaurin series. So we get sine of x equals a plus b x squared plus c x cubed and so on, where a, b, c are coefficients. You can put in the Maclaurin series formula and you will get figure it out. Now we can use this polynomial to find the value of anything, like sine of 3 plus 2i. You may ask that why we are using this. We can use any other things, like there's infinitely many things we can use. Like in real axis, we can just do normally, and if it is a complex number right here or pure imaginary number right here, we can just take it 0 or infinity or anything we want. But what we gotta do is we gotta say that sine of x must be differentiable everywhere, like not like an modulus of x. This is y-axis, not imaginary axis, and this is x. It's not differentiable. So there's this point here where we get two different slopes, like here and here. Minus 1 and 1. There we can just extend this sine of x in the only one way, which is it must be differentiable in everywhere. And in the same way we can find the value of functions like e to the x or 2 to the x, anything which is not defined in the complex axis. So if we write the Taylor series of e to the x, we get the value of e to the x at 3 plus 2i or whatever you want. So this is used to find Riemann zeta functions value, like zeta of -1 equals -1/12, which is nonsense because we get 1 plus 2 plus 3 plus 4 and so on up to infinity equals to -1/12. But it does not make sense. It is a divergent series. So what we are doing here is, we know that if we draw the complex axis, I mean input plane of zeta function, I'm sorry, and this part is 1, we get, we can define any points right here, but anything this below this line is, it blows up to infinity, I mean it approaches to infinity, so it won't work out. So what we are doing here is we are writing the Taylor series or Maclaurin series of the zeta function. So before I discuss about the Maclaurin series of the zeta function, I'll explain you the analytic continuation of an function for which it has a singularity. First of all, I need to explain what is singularity. Singularity means, for example, if I do the same thing for tangent of x, tangent of x graph is like this. It's not imaginary axis, it's normal y-axis, and this is x-axis. So if I draw the graph for this tangent of x, I get this graph. And I'll get many strips like this. It's negative pi by 2, it's 0, it's pi by 2. So we learn in school that tangent of x when x is equals to pi by 2 is equals to infinity, but it could not be, it could also negative infinity. What we are doing here is we can't write the value of tangent of pi by 2, but we can approach it to pi by 2 like tangent of pi by 2, not like this. We can write a limit form like limit x approaches to pi by 2 tangent of pi by 2, and if it is from this direction it's gonna be infinity, and it's from the opposite direction it's gonna be negative infinity. I mean here it comes x. So we can't write analytic continuation for this. So if you try to do that, like this is a imaginary axis, it's imaginary plane, it's real plane. So now if we write the Maclaurin series of the tangent of x, we can describe the value of tangent of x in the unit circle. It's pi by 2 and this is negative pi by 2. We can only describe the tangent of x in this unit circle, and that's a problem. So what we can do is, if we try to put the point right here in the Maclaurin series of this, we get divergent, like each term differs like thousands of values, like third terms approximate to 1000 plus 10i, and the fourth term will be negative 1000. So we get some nonsense values. So what we are gonna do here is we are gonna find the value like at this point. So here is a singularity and here is a singularity, so we get another unit circle if you write the Taylor series of the tangent of x at this point. So we get the unit circle like this. So the unit circles depends upon the where the singularity is. So if the singularity is the distance between the singularity and the Taylor series where we are centered at, so let's say this is r, so the radius of this unit circle must be r. Anything outside this unit circle is not defined. So we can write this point and we can find this and here, and like that if we do everywhere we get the value of tangent of x even at 15 plus 30i. Now Riemann zeta function, has a singularity at this point 1. So how to find the zeros is, there's a lot of form of Riemann zeta function. We can write the Taylor series of the zeta function at this point, and we can get this unit circle with the radius of the singularity of this 1 and this where we are centering the Taylor series value. So this is r, so the radius of the circle must be r. Now we can keep a point right here, and we can write the Taylor series of zeta function with respect to this point, and we get this unit circle, and it's little bit extended right here, and we do that forever. We can describe the value of the zeta function even like -1, which must be infinity, but it's not. Zeta of -1 is equals -1/12. You might think that it makes nonsense, so what we are making here is it's differentiable everywhere, and that's how analytic continuation work. So thanks for watching. Goodbye.